Right, let's finish up kinetics. So this is part 4 of the kinetics video, and hopefully uh, this breaking this lecture part will kind of help you guys out a little bit. So let's start with a little discussion about law versus theory. We're going to talk about reaction mechanisms, molecularity, and we're going to look at some enzymes. So kinetics gives what happens. That's what the first sentence on this slide says. And basically what we're saying is when we look at the rate law, what you're looking at is a mathematical description of what is actually going on in your flask. If someone asks you why you observe that rate law, well, then we have to describe what's going on using a mechanism. And a mechanism is a theoretical, stepwise description of how reactants become products. Now, reaction mechanisms can occur all at once in one single step. They can occur through several discrete steps, and each singular step, each process, is called an elementary reaction or an elementary process. Now, molecularity is a descriptive word that we use to tell how many molecules are involved in each step of the mechanism. Now, earlier I told you that a lot of times those MN numbers on the rate law were 0, 1, 2, 0, 1, or 2. And the reason for that is that unimolecular activities where one molecule is involved is very common. Bimolecular um, uh, reaction steps where two molecules are involved, very common. But termolecular, where three different molecules are involved, are rare if they actually happen at all. Um, I think I don't know enough about that topic to make um, an informed decision as of the science today. But from what I remember as a student, there were no examples of termolecular reactions that we looked at that were solidified as like really, really, really definitely termolecular. There was always some discussion that they may be a bimolecular and a unimolecular step. But the ones that we're going to look at least in AP, are all going to be unimolecular or bimolecular step. And this first bullet point on the slide really just tells us why termolecular is so uncommon, if indeed it even happens. And that's because you have to have multiple molecules, in this case 3, colliding in the proper orientation and with the proper energy. So the 3 molecules have to be, out of all of the possible microstates they could be in, they have to be in the one microstate where a reaction occurs. And with 2, that's okay. With 3, that's very unlikely to happen. But if we go back to this chart, we can see the rate law on the right that comes from knowing if something is unimolecular, bimolecular, or termolecular. Now, as you've watched these videos, hopefully you've watched them 1, 2, 3, and 4 in a row to start this unit out. You didn't just stop. You may have wondered, hey, where am I getting, like, how do I know it's a 2 as an exponent or 1 as an exponent? Well, I knew if the step was unimolecular or bimolecular, and that's what's going to tell me the reaction that I need to put there, the exponent I need to put there. Now, what might limit the rate, right? When we're looking at multiple steps, there has to be one step that, or the steps don't have to move at the same speed. In fact, they don't move at the same speed. So one of the 2 steps is going to be the slower step, and that's going to be called the rate determining step. And the book likes to use the bottleneck description, and that's fine. You have 2 steps, toll plaza A and toll plaza B. If uh, the toll stops everybody at A and B is like an easy pass and everybody goes through, well, then toll plaza A is the rate determining step, right? I don't like that because we don't have tolls around here. So think back to we learned about the theoretical yield, right, and the limiting reactant. And the limiting reactant was the one that ran out first, right? It's a similar concept, right? The step that's going to determine the rate goes the slowest, just like the reactant that was going to limit how much product you can make was going to run out first. So we're looking for the slowest rate in order to get the rate determining step. Now, what kind of bullet points, what kind of criteria do we need to meet to have a plausible mechanism? Well, we've got to be able to derive the rate law from our mechanism. The stoichiometry that's in the mechanism has to harken back to the original reaction. All the steps have to balance, so just like any regular old chemistry equation. If there are intermediates that are formed, they have to be used up. And if you have a catalyst, it must be regenerated. So that means it cannot be changed by the end of the reaction. So let's look at a mechanism with a slow initial step. So my overall reaction is NO2 plus CO yields NO and CO2. So I'm looking at nitrogen dioxide and carbon monoxide, and I'm forming nitrogen monoxide and carbon dioxide. Now here's the rate law. Rate is equal to K times the concentration of NO2 to the second power. Well, if the first step is going to be the rate determining step, then the coefficients on the reactant side are the same as the order in the rate law. And so what are my coefficients? Well, it's telling me right here, because CO2 is not involved, that CO2, when they did their experiments to determine if the rate changed when they changed the concentration of CO2, CO2 did not affect the rate. So we're really just looking at nitrogen dioxide here. So the first step of the mechanism begins when two molecules of NO2 react with each other. And when they do that, they're going to form an intermediate, NO and NO3. Now, I'm trying to make, one of these two things right here, one of my products in my first reaction. And since two molecules of NO2, of nitrogen dioxide, are reacting, the only thing I can try to make that is a product is NO, right? Nitrogen monoxide. Well, in order to balance everything out, that means the other thing I have to make is NO3. But the thing is, when we look at the given equation, right, we don't see any NO3. So where is that coming from? Well, it's an intermediate. And that means that there must be a second step that gets rid of that NO3. So what we're going to do is we're going to take the first step, which is the slowest step, and that's going to identify our rate law. The second thing we're going to do is we're going to add up those two steps, and we're going to make sure that the steps balance, and we're left with the reaction that we started with. So let's take them and do that. So remember Hess's law, and this is very similar to Hess's law. I'm just going to see what cancels out. So if it's on both sides of the equation, well, then it will cancel. And sure enough, this is what I get. So here are the two elementary steps that I've put forth as a mechanism. We see an NO3 on the left and an NO3 on the right, so it cancels. We see an NO2 on both sides, so it cancels. And I'm left with NO2. Wow. NO2 plus CO yields NO and CO2. And that matches what we started with. So there we go. Because it balances out and everything works, this would be identified as a plausible mechanism. So that's a slow initial step. Now let's look at a mechanism with a fast initial step. So we're going to look at the reaction between nitrogen monoxide and diatomic bromine in order to make NOBr. Now, in this reaction, our rate law is KNO to the second power, Br2. And we look at that and I say, well, all right, I have two molecules of NO and one molecule of Br. That's three molecules. That's term molecular. And so I look at that and I go, probably not, right? We know termolecular are rare if they happen at all. And so the rate law is probably suggestive of a multi-step mechanism, right? More than one step. So what might that be? Well, because the overall reaction is at equilibrium, we kind of identify that equilibrium is going to be established quickly, and then there's going to be a secondary slow step. So we're going to put forth this idea. Here's our original equation, 2NO plus Br2. So we're going to write that down. We'll put it up here. 2NO plus Br2 yields at equilibrium 2NO Br. Well, our first step, our fast step, is NO plus Br2. We're just popping them together, and we're making NOBr2. And then our second step, we have NOBr2 plus another molecule of NO, because again, two of them have to react in order to get NOBr. Now, the NOBr2 is a problem because it's an intermediate, right? We have to be able to explain it. So we got to look back at our rate law. The rate law tells us that the overall reaction is going to depend on the rate of the slow step, right? And so the rate law for that step must be the rate of K, all right, times the concentration of NOBr2 times the concentration of NO. But here's the thing. NOBr2 is an intermediate, so how do we find the concentration of an intermediate that we didn't put into the reaction in the first place? How do we figure that out? Well, there's two ways we can go about it. We have to look at how it reacts. It can react with NO to form NOBr, or it could decompose to reform some NO and some Br2. The reactants and the products of the first step are at equilibrium with each other, that first step that we kind of put forward. And so what we're going to do is we're going to actually set them equal to each other, and we're going to solve. And the reason that I can do that, and we'll look at this more in the next chapter, is the forward rate is equal to the reverse rate. And a lot of times we write that like this. K1 is equal to K sub negative 1, where this is the forward rate and this is the reverse. And so since I'm telling you that we can do that, all right, let's do it. K1, the forward K, times the concentration of NO times the concentration of Br2 is equal to the rate of the reverse reaction times the concentration of NOBr2. And we can solve this for NOBr2's concentration. So we did that. I just moved it around, and I get the rate is equal to K2, all right? And you can read the rest. I'm not going to read it to you. When we solve that out, when we simplify it, we actually get the observed rate law, the rate law that we had given to us in the very beginning. And because of that, that tells us this these two elementary steps is a much more like probable mechanism to explain this reaction than if we were to try to explain it as a termolecular step happening in one step, termolecular reaction happening in one step. So there's a slow first step and a fast first step. Now, we will see some more of that K sub 1 and K sub negative 1 in the next chapter. But for now, all you need to know is that the forward and reverse rates are equivalent. Now let's finish this lecture up by talking about some catalysts. And, I like that Kinetics finishes with catalysts because, you've seen a bunch of new information, and catalysts are something that you've been learning about since biology. And so it's nice to kind of wrap up with a look at something we're familiar with. So we know that catalysts increase the rate of a reaction by decreasing the activation energy. And we've already talked about how they may do that, right? They're going to change the mechanism by which a process occurs. Now, there's three types of catalysts. There's homogeneous catalysts, heterogeneous catalysts, and there are enzymes. Homogeneous catalysts are identified when the reactant and the catalyst are in the same phase. So, if you have two gases and one of the gases is acting as a catalyst, that would be a homogeneous catalyst. Now, sometimes we'll take the reactants and the catalyst and we will dissolve them in the same solvent. And that basically is the same phase, so to speak, right? They're both suspended in the same solution. Now, this bromine reaction here is actually pretty interesting. I wanted to write it out. They don't write it out in the slideshow here, but I'm going to write it out. So let me grab my pen. I wrote it out on some scratch paper. Scratch paper is good. So let's move this down a little bit. And we'll see if we can get in there. So here's the steps. There's two steps to the breakdown of this hydrogen peroxide. So we're breaking down hydrogen peroxide in the presence of bromine. So here is the actual reaction. It's breaking down 2H2O. And we have 1O2. So there is our overall reaction. Well, let's look at the steps. There's two steps. We have 2Br minus, and it's reacting with hydrogen peroxide. and 2H plus ions to form Br2 and 2 waters. So there's our first step, step 1. And here's step 2. We have Br2, bromine, reacting with H2O2 to form 2 Br minus, 2 H pluses, and an O2. All right, well, let's look and see what's on both sides. 2 Br on the left, 2 Br minus on the right, Br2 on the right, Br2 on the left, right? 2H plus on the left, 2H plus on the right. And I'm left with 2 H2O2, all right, breaking down into 2 waters and 2 oxygens, which is exactly what we should have from our initial given reaction. Now, this identifies bromine and the intermediates of, well, let me take that back. This identifies the bromine ion, right, as the catalyst here, and the Br2, the diatomic bromine, as an intermediate. And so since we regenerate our bromine ions, they don't change overall in the course of the reaction, it is our catalyst. Now, there are also heterogeneous catalysts, and this is a catalyst that exists in a different phase in the reaction than the reactants, rather. Now, a lot of times we'll see this in organic chemistry. Palladium and platinum are pretty common catalysts in organic chemistry. And what we typically do is pass a gas over a solid surface. A great example of this would be your catalytic converter in your car, which gas from the engine is going to pass over that metallic surface. So the adsorption, which is a word you have not seen since we did the lab at the very beginning of the year on chromatography. So the adsorption of the reactants is the rate determining step the majority of the time when we have that metal or that solid phase catalyst and another phase as our reactants. Now, enzymes are definitely worth mentioning. Enzymes are our biological catalysts, and hopefully you remember way back to biology that they have a region where the substrates are going to attach to. That's called the active site, and the active site is actually the place. Sorry, I got a phone call there. What I was saying was the region where 2 reactants or more reactants attach on the enzyme is called the active site. Now remember, the lock and key model is a pretty common way that we teach biology students how the enzyme and the substrate bind together in order to come up with new products. This is a really specific description and is probably not as accurate as the induced fit model, where molecules in 3 dimensions actually changed based on the polarity or non-polarity of regions on the substrates in order to lock them in place and then twist them around, bend and stretch those bonds and move them. All right, so hopefully that kind of helps you get through chapter 14. This will wrap up the last video on chapter 14 for me. So if you have any questions, let me know, and I'll be glad to give you a hand.